Hello and welcome to Module 1 of your physics course. In this module, we're going to cover speed, velocity, and acceleration. You can find this module on pages 1 through 29 in your textbook. So let's get started. Today, we're going to cover the first half of Module 1. We're going to go all the way to example 1.6. The first half of Module 1 is going to be math review. So, you probably have covered this in a math course before. If you did Apologia chemistry last year, you did cover all of these last year. But there's going to be some review before we get started. Just need to make sure that we are all on the same page so we can do well in this course. We're going to review the metric system, the factor level method, units in mathematical equations, making measurements because there is a wrong way and a right way of measuring things in science, the difference between accuracy, precision, and significant figures, how they all work together, scientific notation, and then once we have reviewed all the math, we'll start applying the math to physics, to some problems in physics. So here we go. This is just a page that summarizes all the formulas that you're going to need in this module. I'll be presenting each one of them individually as we go. So you can stop now and copy them if you want to, or just take notes as they appear before you need them for your problems. Okay? It's up to you. This is a video. Make it work for you. Know that in your textbook, anything that is bolded is a vector. You may not know what a vector is yet. If you have not done trigonometry, you don't know what a vector is probably. We'll be working with vectors this year, and I'll teach you about vectors, what you need to know in Module 3. What you need to know right now is that a vector is a quantity, has a numerical value, so 20 miles per hour, like that's speed, but it also has information about the direction, so 20 miles per hour, east, west, north, south. And you do that by assigning a positive or a negative sign to that quantity. So that's what a vector is a quantity plus a sign that has information about direction. Okay, the metric system. The metric system is used in science because scientists have agreed to use the metric system. It is a very easy system to use because it uses powers of 10. So you multiply by 10 or divide by 10, which makes it into very easy computations. I'm from Europe, so I grew up using the metric system. I know that you had to learn it in school, so hopefully you're pretty good at using the metric system because you're going to be using it this year. But the beauty of the metric system is that it has lots and lots of different units. And you go from one unit to another by multiplying or dividing by 10. And you start with a base unit and add a prefix to it, and then you have changed your base unit. For example, imagine that we are measuring mass. So the base unit for mass is grams. So you can have kilograms, hectograms, decagrams, decigrams, centigrams, or milligrams. Okay, that's what I mean by pick up this prefix and add that prefix to the name of the base unit. And when you do that, you have a new unit. So in this ladder, anything that's at the top is bigger than the things that are at the bottom. So kilo is bigger than hecto, hecto bigger than deca. Milli will be the smallest in this group of units. There's a lot more going down and more going up. But these are the ones that we're going to use the most. So how does this work? Well, imagine that you want to know how many grams you have in a kilogram. Well, how many bumps are there between the two of them? 3 is 3. Multiply 10 by 10 by 10 is 1,000. So there's 1,000 grams in a kilogram. Okay? The same thing going down. How many milligrams in a gram? Well, they're separated by 3 bumps. 1,000. How many centigrams? 100. Okay? You also can go the other way around. So you want to know, for example, how many kilos are in 1 gram? Well, you would divide by 1,000. You would have 0.001 kilograms in 1 gram. So this is what you need to know about the metric system. You may want to copy this page if you are not very familiar with it, but you're going to be using it. So please make sure that you know how to go up and down the ladder. Now, the factor level method of conversions is just a fancy name for a very simple method. The factor level method helps us go from one unit to another between prefix units within the metric system, or from the customary or English system to the metric system. Okay, for example, kilograms to grams or feet to meters. It helps us to go from one unit to another. To be able to do that, you need to know the conversion factor. That means, how are they related? How are kilograms and grams related? How are feet and meters related? Here you have a few of them. In 1 inch, we have 2.54 centimeters. That is a conversion factor. That's how they are related. In 1 pound, there are 454 grams. That's not a conversion factor. That's how they are related. These are 1,000 grams in 1 kilogram. That's how they are related. That's the conversion factor. If you don't have the conversion factor, you cannot go from one unit to another. And how does this work? Well, imagine that you want to know how many meters are in 5 kilometers. You always start with the number they give you. You write it down. You open a fraction line. Okay? You write the old unit that you're trying to get rid of at the bottom of your fraction. You write the new unit at the top of your fraction. And then you write the numerical connection between the two units. There's 1,000 meters in 1 kilometer. That's one way to do it. You also could have put 0.001 kilometers in 1 meter. Different people do it differently, but the relationship has to be true for this to work. Okay? Now, sometimes you're going to see the multiplication sign. Sometimes you're not going to see the multiplication sign. There's going to be a dot or nothing is going to be there. But if you have a fraction, there's a multiplication between the two of them, the two numerical values here. Okay? So anything that's at the top is multiplying. Anything that's at the bottom is dividing. In this case, if you don't have a 1, the 1 is implied. It's like having an x. If you have an x in algebra, you have 1x. From algebra, you should also know that if you have something at the top and something at the bottom, okay, they cancel one another and this becomes 1. And 1s do not change anything. They don't change when you multiply or when you divide. Okay? So 5 times 1,000 divided by 1 is the 5,000 meters that you have here. And this is it. This is the factor level method. It's your turn to try this. I'm going to give you the answer for this problem. If you got it right, move on. This is a video, just skip forward. If you did not get the answer correctly, you can see me solve the problem for you. This is on page 2. So everybody, we're on page 2 in your textbook. And it's asking you to change the mass from 4,523 centigrams into kilograms. Okay? According to the book, let me get here into the whiteboard. According to the book, you should be getting 0.0452 kilograms. Okay? So this is your answer. If you got this, you got it right. If not, let's see how it's solved. You started with the 4,523 kilograms. That's the number they gave you. You always start with whatever they gave you. You open a fraction. Remember I said sometimes you put a multiplication sign, sometimes you just leave it blank, but it's implied that it's there. So you start with I put kilograms and it should have been centigrams. Okay. You start with the units that you are trying to cancel at the bottom and the units that you want at the top. And then you think, how are they related? Well, they're not related directly. If you go back to the scale we saw a minute ago, the ladder I showed you in the prefixes, you'll see that there are several bumps between kilograms and centigrams. So you can count the bumps if you have it in front of you, or you can do it the way I'm going to show you next. So let me erase these right here and say, let's go first to the base unit. It's always easier if you go to the base unit. And then you can go from that base unit to the unit that you need. This gets canceled because they are opposite one another. Multiplying here, dividing here, cancels, becomes 1. And you're left with the kilograms that you needed. Okay? So now I can think this through. How are these two related? Well, I know that there are 100 of them, 100 centigrams in 1 gram. Also know that there is 1,000 grams in 1 kilogram. Now I have all the information I need. I multiply everything that's at the top, so this 4,523 times 1 times 1. The ones don't change anything, so you're left with this number. Divide by 100 and divide by 1,000. Now, if you know how to use parentheses, it's a lot easier to use parentheses. What do I mean? Well, I would open parentheses in my scientific calculator. Sometimes this is a different number, so you have something else multiplying here. That's not a 1, and it changes then the top value, multiplying this 1. And I close my parentheses. I open my division symbol, and I open a new parenthesis, multiply whatever is at the bottom, close my parenthesis, and the calculator will shoot out the right answer. It's important for you to close parentheses or your calculator is not going to do it right. If you open a parenthesis, you need to close the parenthesis. Also, you can use double parentheses, like parenthesis, another parenthesis, another parenthesis, and another parenthesis. Your calculator is able to read these. So you do whatever you need to do here mathematically and put it all together with more parentheses. Please make sure that you know how to use your scientific calculator. You can go to YouTube, search the name of your calculator and how to operate your calculator. Search those words, how to use whatever the name of your calculator is, and watch the videos that are posted there because you're going to use it a lot this year. Let me clear these and go back to instruction. Now, it's very, very important in science for you to know how to measure things. There is a right way of measuring things and a wrong way of measuring things. Number 1, you need to use the right tool. The instrument that you use needs to be used for whatever you're trying to measure. In this case, we're trying to measure the length of the blue ribbon. Okay? So I want to use a ruler. And you're going to be using a lot of rulers. So the second thing that I need to pay attention to is the units. Once I have a tool, I need to check to see what units the tool uses for measuring. Because you're doing science, you need to be using the scientific, the metric system. Okay, the metric system uses centimeters and meters and kilometers and so on. So no more inches in your rulers, centimeters. Okay. So the third thing I need to pay attention to is the scale. I need to be careful with the scale. So I know how to read the scale in my instrument, in my tool that I'm using for measuring. Please notice that the scale of the 2 rulers is different. Here we have lots of little lines. Each one of them is a millimeter. There are 10 of them in a centimeter. Right here, I only have 5. That means that each one of these little lines is worth 2 millimeters. What does that mean? That means that I can get closer to the true value with this ruler than I can with this ruler. Look at this, 4.96 centimeters versus 4.9 centimeters. This is precision. The more digits you can give me after the decimal point, the more precise you are. Okay, we're going to talk about precision and accuracy in a minute. But just know that the smaller the scale of an instrument, the more digits you can give me after the decimal point. And that makes that instrument a better instrument. Okay? So a smaller scale makes the instrument better. Let's look at this. When you have 10 little lines, if we look here, okay, you can read up to the millimeter, the 10th position. I know that this is 4, and then I have 9 more little lines. Now, between the 9th line and the next centimeter, I have to guess. Well, somebody could have guessed 4.96. Somebody could guess 9.97. It's up to you. The last digit is a guess. When you measure in science, you always give me one more digit than the scale can read. That's how we do things. Look at this scale right here. In this instance, the scale is accurate up to the unit, up to 4 centimeters, so up to here. The next digit is a guess, because I know this is 4.2, 4.4, 4.6, 4.8. But after that, I'm guessing, and I guess it was a 9. So I was accurate up to this point. I was precise up to this point. I'm sorry. I should be using my science words correctly. I know that in everyday speech, we use them interchangeably, but they're not the same. And you're going to see in a minute, they're not the same. So this is my guess. Okay? And in science, when you're doing your lab experiments at home, you're going to need to do that. Give me one more digit than your tool can read. Let's look at that. Accuracy versus precision. What do we mean? Accuracy means how close to the true value did you come when you're reporting data. To be able to know if you were accurate, you need to know the standard. You need to know what the true value is. If you don't know where the bullseye is here, you cannot hit the bullseye because you don't know where it is. Okay? So you know you're accurate if you hit the bullseye. You got the same number as everybody else got. Okay? The true value. Here it is, an indication of how close a measurement is to the true value. And you don't know that unless you know the true value. Okay? Okay. Precision. On the other hand, precision is getting the same number over and over. Okay? You may not have hit the mark, but here is your bullseye and you didn't hit it. Okay? But you got the same number over and over. You remember that in science, often scientists do an experiment several times and then they average the results. Okay? That's what it's showing here. Lots of different tests being done, getting the same result over and over, but you did not hit the mark. Precision has to do with the instrument that you're using for measuring. So the smaller the scale of your instrument, the more precise you can be. Doesn't mean that you hit the mark, but the more precise you can be, the more digits you can give me after the decimal point. Why are you getting the wrong result? Maybe you don't know how to use the tool. Maybe you're reading the tool incorrectly. Okay? So there's a lot of reasons why you're not hitting the mark, but you're being very precise in here. Okay. Let's look at an example. Look at the two scales right here. Okay? They both are measuring the mass of the beaker. This right here says 24 grams. This one says 24.073 grams. This scale right here is more precise than the one over here because it's giving me more digits after the decimal point. It's using a smaller scale. Okay? That's what we mean by precision. How many decimal points can you report after the decimal point? How many digits after the decimal point can you report? The more you can report, the more precise you are. Okay, your turn to think about this. Imagine that you have a football field, okay? And it's 100 yards. Of the three measurements here, which one is the most precise? Stop for a second to think. Okay, if you guess this being the most precise, you're correct. Of the three results right here, this one gives you the most digits after the decimal point. And as I said, precision had to do with digits after the decimal point. That instrument had a smaller scale. Okay? Next, accuracy. Accuracy has to do with, did you hit the standard? This is the true value. Of the three, which one hit the value best? Think for a minute. Okay, did you guess this one? If you did, you were right. Of the three results, this one is the closest to the truth. So the most accurate. You see the difference between accuracy and precision? I hope so. Now, significant figures. Significant figures allows us to make numbers, to carry the precision in our results, in our data, to our computations. And you'll see in a minute how this works, okay? So significant figures, first you're going to have to learn what is a significant figure and what is not a significant figure. But just know that significant figures help us carry the precision from our experiments, from the tools that we're using, the scale. The smaller the scale, the more precise. That information is in your data, okay? Because you're giving me digits after the decimal point. That information can move on with your computation. And significant figures allow us to do that. They allow us to make zero significant, for example. So let's see how this works. And you do have all the rules in your textbook. It's in the cover of your textbook. But I'm going to go over the rules with you. The first thing we need to do is know who is significant and who is not significant if you're a digit. Rule number 1, all non-zeros are significant. So look at this number right here. We don't have any zeros. That means all of them are significant. Count them. 1, 2, 3, 4. 4 significant figures. This one doesn't have any zeros. They are all significant. 1, 2, 3. 3 significant digits. Rule number 2, final zeros to the right of the decimal point are significant. So here's my decimal point. This is at the right of the decimal point is 0, and is at the end. This 0 is significant. This is 2 significant figures. Okay? Before I go over this number with you, I want to read rule number 3. It says zeros found between 2 significant digits are significant. Look at this. This is a significant figure because it's not a 0. This 0 is significant because it's to the right of the decimal point at the end of the number. So it's significant. This 0 was in between 2 significant figures, and now it has become significant as well. So that's 1, 2, 3, and 4 significant figures. So let's read rule number 3 one more time. It says any 0 that's between significant figures is also significant. These are between 2 significant figures. 5 is significant, 1 is significant. Now they both have become significant as well. So that's 1, 2, 3, 4, and 5. This one right here, these 3 zeros between 3 and 5. 3 and 5 are significant. The zeros now have become significant as well. So that's 1, 2, 3, 4, 5, and 6. Rule number 4, zeros as placeholders are not significant. What do we mean by placeholders? Well, are those zeros that help us know the placement, okay? So there's a 1, the tenths, the hundreds, the thousands, the 10,000s, the 100s. So all of these zeros right here, okay, are not significant. This is a to the right. Those 3 zeros are to the right of the decimal point, but they're not at the end of the number. See what I'm saying? And that 0 was not significant because zeros are not significant. Okay, so they don't fall between 2 significant numbers and they don't count. The decimal point is right here. When you don't have a decimal point, okay, it's implied that it's at the end of the number. You could put other zeros after the significant. The decimal point. You could put zeros. So it's right here. And these are not to the right or to the end and right of the number, so they don't count as either. So 17,000 is just for placement. It's for how big is this number? 17,000. That's that. Nothing else to it. So now we want to carry the position of our data into our computations when you're doing math. And there are 2 rules you need to follow to be able to do that. There's a rule for when you're adding and taking away, and there's a rule for when you're multiplying and dividing. And the more you do it, the better you get at it. Okay. So at the beginning, it might be a tiny bit hard to do, but you're going to get really good by the end of the year. So rule number 1 for addition and subtraction says the number of decimal places in the result, so it means in your answer, equals the number of decimal places in the least precise measurement. We're not counting significant figures. Here we are going with placement. So this ends in the 10th position. This ends in the 1000th position. I said to you, the more you can give me, the more precise you are. That means this is the least precise of the 2 numbers. My answer cannot be more precise than the least precise of my numbers. So when I put this in the calculator, it gives me this number. But I cannot report all of these digits. I need to stop in the 10th position. I can only report 3 significant figures because this stopped in the 10th position. Okay? So don't count them. Look at the position. The more you report more precise, don't go with that one, go with the least precise. The rule for multiplication and division requires you to count significant figures. And then you go with the fewest number of significant figures. Look at this, multiplication, okay? Count them, 3, 5, and 2. Okay, 2 is the fewest number of significant figures. So I can only report 2 significant figures in my result. I put all of these in my calculator. It shoots this blue number, and I need to give 2. So I count 1 and 2. I look at the 1 over and think, can I round up? Well, 0 is not big enough to round up. I'm going to leave it at 45. The rules of round up is that you need a 5 or over to round it up. 10. Division. Count them. 4, 3. 3 is less. My answer needs to have 3 as well. Put it in the calculator. It gives me this blue number. And then I say I only can report 3. So 1, 2, and 3. I need to stop right here. I look at the 1 over and notice it's a 9. I have to round up. The 5 has become a 6 now. And these are my 3 significant figures. Please, please, please round up. Okay? Let's look at this. 24 times this one right here is a multiplication. So that means you need to count 2 significant figures, 3 significant figures. I can only report 2. When I do this, the calculator gives me this number. 1, 2, I would have to stop at 8. 7 is bigger than 5. I need to round up. 79 is what I need to report. Once again, multiplications or divisions requires me to count significant figures. 3 versus 2. I need to go with 2. Calculator gives me this. I need to stop at 8. 1, 2, stop at 8. 2 is not big enough to round up. I'll leave it at 28. 3 significant figures versus 3 significant figures. So I need to report 3 significant figures. Here's what the calculator gives me. 1, 2, and 3. I need to stop right here. What happens? This is big enough to round up. Okay? And that is the 3. Because this becomes a 10. Carry over 1. Another 10. Carry over the 1 is 3. Okay. It's your turn. Let's use the two rules to solve these two computations. Very easy computations, but it's all about significant figures. I'm going to give you the answer to these, and if you get it right, you don't need to watch to see how it's solved. But you're going to find these on page 4 in your book. Okay, so let me get the whiteboard here, and let me write it down for you. So for the first one, you should get, let me get white, make sure I have white, 458.60 kilograms. And for the second one, you should get 7.00 miles per hour. Remember that you need to report units. We're not talking about monkeys or bananas. We're talking about kilograms and miles per hour. So why this amount of significant figures? If you didn't get these results, let me box them so you know these are the answers. These are the answers that you should get. So the first one was 546.2075 kilograms minus 87.61 kilograms. Okay, this is a minus or addition rule that you need to apply here, and that has to do with precision. You need to go with the least precise. That means the one that has less digits after the decimal point. This one has less digits. It only has 2. This one has 4. Okay, so you need to stop right here, and you need to stop in the 100ths position. Put it in the calculator, and then you stop in the 100ths position right here. That's how you get this answer. Okay, so for the second one, it was speed. You were trying to calculate speed, and it was a division. So let me copy the numbers, 3.012 miles. And then you're dividing by the 0.430 hours. Okay. So because it's a division, in this case, you need to count significant figures. 1, 2, 3, 4. That's a rule for significant figures. Versus how many here? Remember, this one doesn't count. This is a placeholder. This 0 does count because it's after the decimal point and to the end. So we have 3 significant figures. Okay. Okay, I hope this made sense. Let's move on. Now, scientific notation. In science, we use lots of big numbers and very small numbers sometimes, depending on what kind of science you are studying. So one way to write big numbers or small numbers is with scientific notation. Scientific notation always means a number that has a decimal point, okay, and then a power of 10. It can be a power of 10 to a positive number or a power of 10 to a negative number. When you have a number in scientific notation that has a power of 10 to a positive number, you know that you have a big number. So if you want to translate it into a regular number, what you need to do is move the decimal point to the right to make it bigger. Because 1.5 is small. To make it bigger, you need to move that decimal point to the right. How many times do you need to move it? As many times as the exponent tells you to move it. So it says 4. Here it is. 1, 2, 3, 4. You are moving it right here. And you're filling each one of these spaces with a 0. So it's become 15,000. It's the same number. It's just different ways of writing the same number. Scientific notation versus what you're used to. Okay? Regular notation. The same thing for little numbers. But now, instead of moving to the right to make it bigger, you're moving to the left to make this number smaller. Okay, you move that decimal point to the left. How many times? As many times as the exponent tells you. 4. So here it is, the dot. 1, 2, 3, 4. You put the dot right here. Usually, you don't leave the dot by itself. You put another 0 in front, so you know this dot right here, so it doesn't disappear. And then you fill the spaces with zeros. And this number are the same, scientific notation versus regular way of writing it, okay? But what scientific notation does for us is allowing us to make zero significant. And you'll see that as we go and practice problems, how that works. Now, we just reached the point in our module when we start working on physics. No more math review. Now we're learning physics. We're going to be learning about distance, total distance versus displacement, two different things. Speed and velocity, two different things. Average versus instantaneous velocity. Acceleration, average and instantaneous acceleration. So this module covers these topics in physics. Okay, what's the difference between distance versus displacement? Well, distance, the total distance, is the total length traveled. You keep adding miles. Are you going forward, then backwards, then all around? Just keep adding all the miles of your travel. That's your total distance. Displacement, on the other hand, is a change in position. So it doesn't matter if you start at A, you end at B. The distance between them is your displacement. It doesn't matter how many curving, walking, running, whatever you did here all around. You end at B. The distance between the 2 points is still just a little space. And I'll show you a drawing in a minute to help you understand that a tiny bit better. Now, the distance right here is used to calculate speed, and it's always a positive number. Notice that both of them have the same kind of units of length. So you have inches, meters, kilometers, miles, centimeters, inches. I don't know why. Oh, sorry, not inches. But anyway, some of them are metric and some of them are in the customary system. But they are units of length and they are shared between the total distance and displacement. Displacement, on the other hand, is a vector. Okay, so it has a quantity associated with it, but it also will have a positive or a negative associated with it that indicates a position. And you'll see in a minute how this works. And it's used to calculate velocity. So it can be positive or negative, and is for velocity. Let's look at this in a tiny bit more detail. So here you go. A, B, the 2 points. You are traveling to B from A. You took this path to get to B, maybe because there was a lake, maybe there was a big tall mountain you could not go over, but that's the path that you took. You keep adding the miles, and that's your total distance that you travel. Now, the difference between position A and position B is your displacement, okay? And that's a vector. This is called a scalar quantity, because it has a numerical value, but it doesn't tell you if you went east or west. In the displacement, you would have to tell me with a positive or a negative, or by writing, what your direction was. And right is going to be positive, left is going to be negative, up is going to be positive, going down is going to be negative. And you'll see this when we work on the problems. So please know some examples of scalar versus vector quantities. We said a scalar quantity has a magnitude only, so it does not give us information about direction. Temperature, mass, time, and speed are all examples of scalar quantities. The vector, on the other hand, is a magnitude, it has a numerical value, but it also gives us information about direction. So we have a force. You're going to be working with forces. This is physics a lot. Displacement, and please notice that it's not the same as total distance that you traveled. It's a different thing. Velocity is not the same as speed. Actually, velocity is speed with a direction, and then acceleration. Now, formulas to know for the little bit that we're going to be covering next. Total distance, you abbreviate total distance, that big long word, with this symbol, which is delta of d. Delta of d is the total distance, and you find it by adding all of those miles, meters, or kilometers, or whatever unit of length you're using, keep adding them, and all of them together is the total distance. Okay? The total displacement is delta of x. Okay, so when you see delta of x, we're talking about total displacement. And in this case, this is a vector, and you're going to have a quantity, a numerical quantity that has a sign. It's going to have a positive or a negative. Positive is going to be to the right, negative to the left. If you're traveling up, it's going to have a positive sign. If you're going down, it's going to have a negative sign. So signs are going to be important here to denotate a direction. Okay? Here we go. Let's see how this works. Let's put it all together in our heads. Example 1.1 on page 8 in your textbook. It says a child is 5 meters away from a wall and rolls a ball towards it. The ball hits the wall and bounces back, rolling 3.3 meters before coming to a halt. What is the total distance covered by the ball, and what is the ball's displacement? So let's get started. How do we do this? Let me clear this, get a new page. Nope, that's not what I want. Here, new page. Okay, here we go. In physics, it's always a good idea to draw what they're saying to you. There was a drawing in the problems, but sometimes it's a word problem and there's no drawings, and you're going to have to draw so you can visualize what's going on. So I'm going to put a dot to show the girl. You don't have to be a good artist to do this. A dot works, okay? And then the ball traveled. And how long did it travel? Well, it traveled 5.0 meters. And then it hit a wall. Okay, just put a line right there for the wall. And then it bounced back, and they said that it traveled another 3.3 meters. And then you had two questions. The first one was the total distance. The total distance. Okay, but I'm going to put 2D, but that means what? It means this, okay? Total distance is this. Okay. And I said to you, when you want to know the total distance, the only thing you need to do is add all the miles, meters, kilometers, whatever the path is for the object that is moving. So that's 5, and then it keeps rolling to 3.3. Add them up. So we have 5.0 meters plus another 3.3 meters. And if you put all of this together, is 8.3 meters. That's your total distance for this ball. What about displacement? Remember, the displacement is a delta of x, and that's a vector. That means the direction of the movement is important. And I'm going to put it in green. So I said to you, okay, please keep this in mind always. If you go in that direction, your movement, it has a positive sign. If you're going to the left, it's going to be a negative sign. Going down, you give it a negative sign. Going up, you give it a positive sign. So do that. This one, the ball rolling forward, has a positive sign. The ball moving backwards has a negative sign. So when you're calculating this vector right here, the total displacement, you need to take into consideration the signs. Let's do that. So positive 5.0 meters minus 3.3 meters. Because what you're calculating is actually this right here. You're calculating the displacement. Okay, this area right here, that's displacement, where it started, where it ended, and this is a displacement, and you do it this way. So when you do the math for this, 1.7 meters is your answer for the displacement, the total displacement. Okay, now you are going to try these on your own. Extra practice problems are found on page 563 in your textbook. It's a good idea to have a tab there that you can move forward as we move along with the modules to indicate where your extra practice problems are, so you don't have to every single time find that page, okay? So start with practice problem, extra practice problem number 1. Pause it, try it. I'm going to give you the value. If you got it right, move on. If not, watch to see how it's solved. Or try again if you want to before you watch the video on how to solve this problem. Okay, let's see. Let me get my numbers. If for number 1, for extra practice number 1, you got this value, 130 feet for the total distance traveled, and minus 30 feet for your displacement, you're done. Those are your answers, okay? So these are the 2 answers that they were looking for. Now, if you didn't get these, you can try again on your own or watch me solve it for you. Okay. The total distance, remember total distance, is adding everything in the problem. The first thing you should be doing is drawing the problem so you understand what's going on. I'm going to draw it right here. There is a person that throws a ball up in the air. How much up in the air? Well, this right here is 50 feet, okay, according to the problem. And then the ball also has to travel this distance of the cliff, which is 30 feet, okay, 30 feet. So the first thing you need to notice is that for a ball to go up and then end right here at the end, at the bottom of the cliff, the ball had to do this. It had to go up and then another 50 feet to reach back where it started, the top of the hill, and then it had to travel the extra 30 feet of the cliff. So this is the path of the ball. Follow the path of the ball to calculate total distance. 50 up, then 50 down, and another 30, and add them up. Add them up. So let me do that for you. 50 plus 50 plus 30. Now this is in feet, okay? And if you do that, that's going to be the 130 feet that you should be getting. Okay. If you have questions, you can always ask me when we have our virtual meeting. So how do we calculate the displacement of that ball? Well, I should not have taken out the drawing. Let me put the drawing again here. Okay, so this right here was 50 feet. Drawings are friends in physics, so that's where it reached and then came down. So now they want to know the displacement, and remember that displacement is a vector, and that means the direction is important. So let's give them values. Going up is positive, then it went down, the 50. Going down has to be negative, and then the extra 30 is also a negative number, okay, because it's going down. Now you need to put all of these together, okay? So your displacement is positive 50, negative 50, another negative 30. Those 2 are gone because they cancel each other, and you're left with those 30 feet that you needed for your answer. Okay, hopefully this makes sense. If not, ask me questions. You can always email me during the week if you have questions. So let me clear these for the next time we need this page. Go back to instruction. Okay, the difference between speed versus velocity. They are 2 different things. I know that when we talk, we use them interchangeably, but they are not, in science, they are not the same thing. Speed is a scalar quantity. It has a numerical value. It tells you how fast you are traveling. For example, this car says here that it travels at 20 meters per second. Okay. Well, velocity, it's a speed that's been given a direction. Look at this, 20 meters per second east. East, you could have also put a positive in front, and a scientist would know that positive 20 meters per second was east, was going that direction. Or maybe you were going up, but the cars don't usually go up, okay? So know the difference between speed and velocity. Speed, scalar, velocity is a vector. Speed doesn't require direction. Velocity is speed with direction. Now, let's put it all together. To calculate speed, you only need the total displacement, and you divide it by the total time it took you to travel that displacement. So this is the formula to calculate speed. Velocity, on the other hand, is a vector. Because I said to you, if part of the equation is a vector, that makes the other that you're calculating also into a vector. And you need total displacement to calculate velocity. So its velocity is displacement and divided by the time it took you to cover that displacement. The two formulas, we're going to be applying them to the next set of problems. So let's see if I can get this out of the way. Example 1.2 says, on page 10, you hop on your bike and pedal 151.1 meters to the end of your street in 25.2 seconds. Turn around and pedal back to where you started. If the return trip takes 27.1 seconds, what is the speed and what was your velocity over the course of the entire bike ride? Okay, let's solve this one. Remember that drawings are your friends, okay? So if they don't give you drawings, you can draw. So you can decide if you're going to give anybody any signs for directions, which you should. So for this problem, my bike is going to be a dot, okay? It's just a dot, doesn't matter. You're going forward, and how much forward? You're going 151.1 meters, okay? And that took you 0.2. It's always important to read the numbers correctly so you don't make mistakes. But we all make little mistakes like this. Just look at it again. And this is seconds. And now it stops right here and returns. Okay. So our distance is the same distance. It's not changed. You go back 151.1 meters. But in this case, we took a tiny bit longer. It says 27.1 seconds. Now, I'm going to go ahead and already give values of direction to my numbers, okay? I know that going this way is going to be a positive number, and then later, going back the other way is going to be a negative number. Just, you may want to do that at the beginning when you start, so you don't forget to do it later. So that's all I know, and they were asking for speed, so speed is going to be one of them, and velocity. Those are your two questions. We don't know. Let's solve these. For speed. What was speed? Use the formula. It says it's the displacement, the total displacement, divided by the time it takes you to travel that displacement. Well, what's the displacement here for the bike? It's going this way and then comes back. So add them up, okay? This right here is a scalar quantity, speed. Speed should be in white here. That's going to make it easier. That means you don't take into account the direction. You just keep adding those miles or meters, in this case, meters. So it's 151.1 meters plus another 151.1 meters. And if you add it up, and then divide it by the total time, I will put this in parentheses in my calculator, and I would do the division. A fraction is a division. Open another parenthesis, and then put the time inside. Total time is 25.2 plus the 27.1 seconds. These are seconds, okay? But you can use parentheses to keep the tops together, the bottoms together, and the calculator will say that the speed for this bicycle is 5.78 meters per second. Remember about significant figures. Adding here, you need to go with the least precise, and that means that you stop at the 10th position, giving your answer up top. 3 significant figures. and the bottom also had 3 significant figures, then you divide it, and it was 3 significant figures, so there you go. That's your speed. Let's try the velocity now. And I erased it a tiny bit more than I wanted, so let me write the time again. That was 7.1 seconds. Okay, so for the velocity is a vector, and it was your displacement divided by the time it took you to cover that displacement. Well, in this case, because this requires you to have direction, those signs are important. And what happens here? Look at this. And here the time. Hope you're noticing something. I hope everybody's noticing that the top is going to be 0. And if the top, sorry, I'm distracted. I keep talking to you and I get distracted. 27.1. So this becomes a 0. Okay, they cancel one another, and a 0 divided by anything is still 0. So 0 meters per second. There's no displacement, you see? You went, but you came back. There's no displacement. I know it's hard to understand this, but from a physics point of view, you don't have any velocity if you don't have displacement. That's it. No displacement, no velocity. You have speed, you just don't happen to have velocity. Now, the problem has a second part to it. So let's clear this for a second. Go back, and let's read the second part to this example. The second part reads like this. A sprinter runs the 200 meters, and they give it to you in scientific notation as well. This little sign, this little cap, means exponent, okay? That's what it means. You're going to see some of these in math, in science too. So this amount of meters in 24 seconds, he then turns around and walks 50 meters back towards the starting line in order to talk to his coach. It takes him 25 seconds to walk 15 meters. What was the sprinter's velocity during the 200 meters dash? What was his velocity on his way back to the coach? And what was his velocity for the entire trip? So 3 questions, 3 different questions. I'm going to draw it for you. Here's your runner, a dot. And what is he doing? He's running forward towards the finish line. Okay, here's your finish line. And how many meters is that? It says 2.00 times 10 to the 2 meters. So it gets to the end. Well, I should put the time it takes him to do that. That's 24 seconds. Okay. I'm writing all the information so I can visualize what's going on. Then comes back 15 meters to talk to the coach. The coach is right here. Okay. And now they want to know the velocity. 3 different velocities. Let's start with the velocity forward to the finish line. Well, what is that? That is the displacement forward divided by the time it took us to go forward. You see that? I'm putting little arrows to show you that I'm going that way. I'm already going to give values for going forwards and backwards. Remember, going forwards positive number and backwards negative numbers. So remember to do that. Go back to white here. So let's look at our displacement. My displacement forward, because this is only going forward, okay, my velocity forward is the 2.00 times 10 to the 2 meters. My time to cover that amount of distance is 24 seconds. Do the math. If you do the math in your calculator, then you'll see that your answer is 8.33 meters per second. Okay, so that is your velocity going forwards. It has a positive value because you're going that way. Okay. Let me erase this so we can do the velocity going backwards. So velocity going backwards. Okay, the velocity going backwards means going that way, equals what? It equals your displacement going that way divided by the time it took you to travel that way. And what is that? Well, that's a negative number because it's going that way. It just means going that way, okay? Divided by the time it took you to do that. And I didn't write it here, but the problem did give it to you. It was 25 seconds. So put 25 seconds right here. 5 seconds. Do the math in your calculator. And according to my notes here, the value is negative 0.60 meters per second. Okay? So what does it mean to have a negative number? It just means that you were going towards where you started your race, okay? Opposite the finished line. That's what it means. That negative just means that you're going to the left, back to where you came from when you were talking to the coach. And now, for the last part of the problem, because this problem had 3 questions, they're asking us to calculate the velocity for the whole thing. So the total velocity, okay, total, well, that would be the total displacement divided by the total time. I hope you noticed that, okay? So what is the total displacement? Okay, what's the displacement here? All of it. Positive 2.00 times 10 to the 2. And then going that way, a negative 15. All these are meters. I don't have a lot of space in this screen, but you know those are meters. And you should probably be writing the meters. And then the total time, the time is 24 going one way, plus the 25 going the other way. That's the total time. Keep things in parentheses in your calculator to help you along. And if you do that, your answer is 3.8 meters per second. Well, what does that mean? That's a positive number. Oh, I can move it that way. That's better. Positive, this positive number, if there's no negative, means it's a positive. Or you can put a positive if you want to. Or just say that is towards the finish line. Okay? When you look at the total displacement, is this area is still in that direction towards the finish line. That's what it means. I hope it made sense. If it makes sense, move on. If it doesn't, email me or wait until we have our virtual meeting to ask me questions. So let me clear this. It's your turn. Let's practice. Extra practice problem number 2 on page 563. I'll give you the answer. If you get it right, move on. If not, watch to see how I solve it. So for number 2 of your extra practice problems, number 2, your answer should be, let's see, actually there are 2 questions. One is the speed should be 9.4 meters per second. And your velocity should be 3.1 meters per second. If you got the 2 answers correctly, you're done. You can move on to the next section of instruction, but if you did not get this information, then you need to watch the video. This is positive because it's towards the refrigerator, okay? That's what it means to be positive. So how do we solve this? Let me get another page. That one is not gonna, okay? Let me get my pen again. And I want white. It's very important for you to read the questions, okay? I'm not reading the questions, but I should probably read the questions to you, even though you read them already. But I wanna show you what I do when I'm reading the question. I start drawing things. Sometimes I read it twice, but I draw what they're saying to me. It says, it takes an infant 3.5 minutes to crawl the 22 meters from the playpen to the refrigerator and 11 meters back towards the playpen. My infant is going to be a dot. I'm going towards the refrigerator. Here you go. And then I go back towards the playpen. The whole traveling took this infant 3.5 minutes. It says here. And if it does not say to give the answer in seconds, you can leave it in minutes. So there were 22 meters here to go towards the refrigerator, and then going back, there was another 11 meters that this infant traveled. Okay, so they want to know the speed and the velocity of the infant. So let me already in my green give values for when I need to find the velocity, so I don't forget to do that. For the speed, I'm not going to need them, but I'll need it for the velocity. So for speed, remember that you need to keep those equations in an equation page, so you have them in front of you when you need them, and keep adding equations as I introduce them to you. But it's good to have them in front of you, so if you forgot how to find something, you can look at the page and find the equation that you need. Is the distance, the total distance, divided by the time it took to do that. Okay, so my speed here is going to be the total distance. Well, 22 going that way, plus my 11 going back, divided by the time it took, 3.5. So when you do that, you get the value that we mentioned before, the 9.4 meters per second. That's where it came from. This is it. Okay. Forward, backwards, the time in minutes. You don't have to change it into seconds. But speed is not a vector, so those two in green, those two signs don't need to be taken into account. Now, you do need to take it into account when you're trying to find velocity, because velocity is a vector. So for velocity, your formula says that you need to calculate the displacement and then divide it by the time it takes to travel that displacement. Displacement means take into account direction. So let's do that. Positive 22 going one way, negative 11 because it's going the other way, and then the time it took to do that. Displacement is this area right here. Okay, this is displacement. Okay, so when you do the math, let me see if I can get the white again. When you do the math, that's where you're getting that 3.1 meters per second. That's positive. Positive because you were going towards, that displacement is still towards the refrigerator. Okay, that's what it means, towards the right, and that's the refrigerator. And that concludes this example. So let's move on. Okay, let's see. Example 1.3 is found on page 12 in your textbook, so let's follow along. It says a jogger runs down a long straight country road at 2.3 meters per second. If she jogs in that direction for 15.3 minutes, how far does she run? Ooh, okay. Oops, I should not have gone that far. I was trying to go, let's see, up here. I was trying to go here. Okay, so remember what I said to you. Remember to draw everything they say to you. My runner is going to be dot. My dot in white. That's my runner. What is this runner doing? Well, it's jogging. And it's jogging this way. It's jogging one way and then the other. Okay. And what are they asking us? They're asking you for the displacement. We don't know what the distance the jogger traveled. Okay, but we know the times. We know the times for one and the other. 2.3. Sorry, that's the velocity of one and the other. Sorry, the velocity of one of the other. 2.3 meters per second. And then on the other way, she was running 15.3. Okay, it is your turn to do extra practice problem number 3 on page 563. I'm going to give you the answer that you should be getting. If you do get the right answer, move on. Videos, very helpful. Can go backwards, forwards, stop. You know, I mean, it's your video. Use it, make it your own, and make it help you. So let's see. Whiteboard again. Let's close these. Okay, I don't want that. I want one of these boards. Why is it not going away? Okay, there you go. So let me read the problem to you first, and I'm going to give you the answer first, and I don't need to read it to you if you did it right. So for number 3, for the extra practice problem number 3, they were asking how much time did it take to run the runner to run the race. So your answer should be 1.0 times 10 to the 2 seconds. If your answer is like mine, you're done, okay? It's number 3. This is number 3. So for number 3, this is the answer. If you did not get this answer, look at the video and see how it's solved. So let me get these right here on another page. Okay, let's see. The problem reads like this. A runner's average velocity over a race of 600 meters is 0.61 meters per second. Since the race was run on an oval track, the runner's displacement was only 62 meters. So my displacement, I'm going to start writing things, is 62 meters. What else did I know? That the velocity equals 0.61 meters per second. They also told me the distance. So they gave me the distance. In a minute, I'm going to see if I need it or not. So meters, okay? And then it says, how much time did it take the runner to run the race? They want to know the time, okay? So the time is your question. Let's see this. They give me velocity and displacement. What do I know about velocity? I know that velocity is my displacement divided by time that it took me. This is the formula that connects the displacement and the velocity together that would allow me to calculate time. I'm not going to need my total distance. I just don't need it to calculate time. But I do need to manipulate my equation so I have time by itself. So time, I don't know what I said to you. It's going to go on the other side multiplying, but then this is going to be bothering me. And to get rid of it, because I'm multiplying, this needs to move down here to divide. So my time is going to be my displacement divided by my velocity. This is the equation modified, so I can find my time. Let me erase some of it so I have some room here. Okay. And then I can put everything in the formula because I have all the information I need. My displacement was 62 meters. And my velocity was 0.61 meters per second. If you put all the information in your calculator, you'll find that the time is the 1.0 times 10 to the 2 seconds that I mentioned before. So that's where it came from. Okay? If you have questions, you can ask me. Email me or Zoom me for the virtual meeting. Here we go. Now, average versus instantaneous velocity. They are two different things. This car is traveling. This graph shows us how the car is traveling. Each one of the points in this graph is the instantaneous velocity for the car. Maybe this is time. Maybe this is time and meters per and time. I don't know. It didn't give us the units here, how it calculated it, but you can find each point of this could be a different kind of velocity. The average is you take them all and you divide it by the number that you use for calculating the average. So it's more constant, okay? But here's a definition. Instantaneous velocity at one moment in time. Every point right here is a moment in time. To find it, find a straight interval in the graph and find the slope. So you're going to have to calculate slope. And I'm going to go over this in a minute with you, how to do that. Probably you have covered this in math, and it should be a review for you. The average velocity is the velocity over an extended period of time. We have been calculating average velocities, okay? But now we're going to learn how to calculate slopes that is going to give us the instantaneous velocity for anything. So you will be performing an experiment at home. It's called measuring average velocities on page 14. If you like to do your experiments as you read your book, when you're assigned to read the book and do your own, so you can stop and do the experiment, or you can do them all at the end. It's up to you. But you're going to have an experiment to practice this. Now, slope, because you need to know how to calculate the slope. This graph is linear, okay? So it's easier to see the slope. But the slope is calculated by looking at the change in your y. This is your y. This is your x. Hopefully you remember this from math. Over the change in your x. What does it mean to have change? Change means that you start with a point forward minus a point before. So when you see a 2 is the final point, y1 is your initial point. The same thing for the x's. So what do I mean? For example, you're trying to find the velocity between 2 and 3. Okay? So if they're asking you, what was the velocity at 2.5? You need to pick up 2 points so you can calculate a slope. You need 2 points to calculate a slope. You're going to pick up a point that's after and a point that's before that 2.5. Okay? This is your point 2. This is your point 1, your final point and your initial point. That's what I mean by 2 and 1. And those have names. The rise over the run is slope. And that just means the rise is the change in that y, how the y change, versus how the x changes the run. You need 2 points from a graph to be able to calculate the slope. Okay? So read the x and then go back and read the y. We'll see in a minute how this works with an example. Things to know, position versus time graphs. This kind of graphs is your velocity. So they give you position and time, velocity. The slope is the change in the position versus the change divided. That little line right here means fraction, okay? Over the time. Find a straight area in your graph. Not all your graphs are going to be straight line. They're going to be curvy. So you're going to have to find the straightest area you can to calculate the slope, okay? And anytime that you have this delta now, when you calculate a slope, you're going to have to do final minus initial. In that case was 2, and the initial was the 1. But that's what it means, final versus initial point. The speed is the greatest where the slope is the steepest. Sometimes the question is going to be, where is the greatest speed? Well, find where the steepest area of your graph is. Going up or going down, doesn't matter. Where is the steepest? The changes in the slope signs indicate the changes in direction. So every time that it goes up and down, it's changing direction. Count how many times that happens, and you'll know how many times it's changed direction. And we'll see this in a minute in our example. Moving the slowest means no slope. If you don't have a slope, you don't have movement. You don't have velocity. So we'll see that. Okay, this is a velocity versus time, not position versus time. So this is actually acceleration, but for this, what I want to talk to you about, it doesn't matter. It went up, it was going up, going flat. There's no change yet, okay? Flat and going in the same direction count as the same. So it was going one way and now it's going down. It has changed direction once because it was going one direction and then it changed once. That's when I said to you, look how it goes up and goes down and goes up again. Those are changes in direction. That's what I meant to you. Now, let's look at example 1.4 and put this information together so you see what I'm talking about, okay? Sometimes examples are the best ways to find meaning in what we're covering. So on page 19, you have a graph. Your graph is better than my graph, so follow your graph. I'm going to open my book to page 19 myself so I can see a better graph as well. Everybody, ready? So you have a graph that looks something like that, and you have several questions. One of the questions says, during what time interval is the speed the greatest? If you remember from the rules that were in the previous slide, 2 slides ago actually, I said to you, you're going to find the greatest speed where you have the greatest slope. So when does that happen? When do you have the greatest slope? Oh, let's look at this. This is some slope. This is a bit slope here too, but here you have a lot of slope. That means that your greatest speed is right here. You see that? Going down. When does that happen? Well, it's sometime between second 10 and second 11. Sometime between those 2 seconds is where the slope is the steepest. And that should be your answer for number 1. Between second 10 and second 11 is when you have the greatest speed. Number 2. How many times did the object change directions? And remember that changing directions means going up and down, okay? That the graph changes direction change by going up or down. So it was going one way, flat doesn't change still, okay? Still the same, okay? Flat means the same. So that was one direction, but then it changes, one change. Still going down, and now it changes again because it goes up. That's 2 changes. Your answer should be 2 changes here. What is the instantaneous velocity at 11.8? So right here between 11 and 12, closer to here. This is flat. This is flat, okay? You cannot calculate a slope, it's flat. So you know that if there is no slope, there is no velocity. That means the velocity is 0.0 meters per second. You have to write 0.0 meters per second. There is no velocity. There's no slope, no velocity. 4. What is the instantaneous velocity at 6 seconds? 6 seconds right here, okay? And you need the instantaneous velocity. You need 2 points, a point before and a point after to calculate the slope here to give me the instantaneous velocity, okay? So I'm going to use the points that the book uses, so you can see that. But basically the points they use were 5. At second 5, they read this to be 4. And then they went to 9. At second 9, they said that it was 0. They use those 2 points to calculate it at that point that they want to know the velocity. So let me write the points that we're going to be using. The points that we're going to be using are for x1 and y1, we're going to use the points 5 and 4. For our point after, point 2, the point we're going to be using is 9, 0. Okay? So in your graph, those are the 2 points we're picking to calculate the slope. And what is slope? Slope is the rise over the run. Rise is just the changes in the y's over the changes in the x's. And this means y2 minus y1 over x2 minus x1. So this is the formula. And remember, keep those formulas in your formula page so you have them in front of you if you don't remember how to do slopes from math. But let's put the numbers in What is y2? y2 is the 0. What is my y1? Well, x and y. This is my y2. So minus 4. Divided by what? My x2 is 9. And my x1, 5. Okay. What number do I get here? Well, I get a minus 4 divided by by 4. So I get a minus 1.0 meters per second. My slope is negative. What does it mean to be negative? It's a vector. That just means that you were going down. Let's go back and see if that's true. Yeah, at that point, you were going down. And that's all it means to be a negative number. So your answer was that minus 1.0 meters per second for number 4. Okay, your turn. Your turn to do something similar to this. Page 563, number 6 and 7. I'll give you the answers. If let's see for a minute. There are graphs. If I give you the answers, no, maybe we just should be going over it. Let's see how we can handle graphs here, because I'm not going to draw the graphs for you. Let me get another page. But if you have the graph in front of you, I will talk about this. You may want to just look at this and see why things are the way they are. 6. So number 6, there are two questions. The first one is how many times it changes direction. Your answer for that one, for the first question, is 3 changes. Okay. B, the second question says, when is it moving the slowest? There are 3 points in which it moves the slowest. At 2 seconds, at 7.7 seconds, or similar, okay? Because you're reading a graph, so it could be done a bit different. And between 13 and 15.9 seconds. So those are places where it's moving the slowest, and that's because all 3 have no slope. No slope. That's how you know. Now, let me see if I can, if you don't know why this is so, if I can draw the graph and I try to explain this to you. Okay, the graph is similar to this. I'm not going to put numbers, but here we go. It goes like this, and then it goes like this, and it goes up, and then it plateaus, and then it goes down. And the 0 is around, let me see, around here is the 0. Okay, so that's the 0 right here. So we said to you 3 changes. What the 3 changes mean is that you change direction by going up and down in your graph. So you were going this way, and then kind of plateauing here, that's 1 change. Then you went up again, that's 2 changes. Plateauing doesn't change anything, and going back down is the 3 times that you change. And for no slopes, you just need to find where it has no slope. So at 2 seconds, it plateaus right here. At 7.7, so closer between 7 and 8, closer to 8, you have another no slope, it's flat. And then you went to another flat place up here between 13 and 15.9. That's what the answers mean, okay, when you look at the graph. Let's look at number 7. For number 7, extra practice number 7, okay, number 7, they wanted the instantaneous velocity at 5 seconds. So if you got this, if that's your answer, you got it correctly, and you're done. You can move on. But if you didn't get this, check out how it's done. Remember that to calculate the instantaneous velocity at any point, you need 2 points to calculate the slope. Okay, your velocity is your slope. So your slope requires you to have the rise over the run, which means the change in the y over the change in the x's, which means this. You need 2 points. Okay, so what 2 points are you going to pick? Well, easy points to read. The points that have easy reads. I'm going to just use the ones that the book uses. Let me erase this right here and just use that part of the equation to write it. I'm going to put it on this side. So 2 points that the book uses are minus 0.5 meters and minus 0.5 meters. And then they divide these by 6 seconds and minus 4 seconds. Okay, those are the 2 points that the book uses. So this is your y. Let me put them right here. Your x1 and y1, and then your x2 and y2. So in your graph, okay, the points that they use, this is your y2. Y2 is going to be here, minus 0.5. And this is your y1. And remember, this is minus y1 is positive. So 0.5. And then this was your x2, so 6. And this was your x1. You put a minus here, is this minus, so the x1 is actually the 4. So 4, okay? So look in the graph, those are the 2 points that they're using, and when you use those 2 points, you get these, and when you do the math, that's where that minus 0.5 meters per second came from. And that just means it's going down. If you look at the graph, that's where it's going down. That just means it goes down. Okay? Great. Let me clear these. And we're getting there. We're getting almost to the end of the section that we need to cover today. Back to instruction. Now, velocity is relative. What do we mean by that? It means it's relative to the person or the object that is observing that velocity. Okay, that's what it means. Let's read this and then try to make sense of it. Okay. To determine the velocity of an object relative to another, we take the velocity of the object being observed and take away from it the velocity of the observer. So we are going to have to do some math here to be able to find out the velocity that's being actually observed by the observer. There's a lot of words like that, but when you see the example, you'll see it's not too complicated. So example 1.5 on page 22. A car and a truck are approaching each other. Okay? The speedometer reads 56 miles per hour, not meters. I tend to say meters because I'm from Europe, but it's miles per hour in the car and 45 miles per hour in the truck. If you are watching, that means you are the observer first. What velocity would you observe for the car and for the truck? And what velocity does the driver of the car observe for the truck and the driver of the truck for the car? Lots of questions here. Lots and lots of questions. So how do we solve something like this? Okay. Let me get my drawing going. So we have a car, we have a truck, and then we have you. Okay. This car is going with a velocity that's, according to the problem, our velocity here. I don't want to copy the numbers incorrectly. That's why I'm looking. 56 miles per hour. And the truck is going the other direction. It's 45 miles per hour. Now remember that these are velocities, okay? Velocities mean that you're going to have to give them direction. It's going to be positive because it's going that way. And this is going to be a negative 45 miles per hour because it's going to the left. Okay. So now they want to know several things. So the first question is, what is the velocity observed for the car. So you and the car. That's the first question. Let's solve that. I'm going to do it in green. Let's start with green and then I'll do different colors. So what is the rule? Your velocity, if you are standing there, your velocity is 0.0 miles per hour, okay? You're not moving. So that's your velocity for you. According to the rule for the relative velocity, to calculate the velocity that you observe, you need to take the velocity of whatever is moving, so our positive 56 miles per hour, and take away from it the velocity of the observer, and that's you. So your velocity here is 0. If you do the math, you'll see that your velocity that you observe for the car is that 56 miles per hour, probably because the car is coming towards you. It's going that way, okay? So that is done. That's how you calculate the first part of the problem. Now, what about the second part of the problem? Let me draw the car again because it disappeared. I'm going to do it in red. So now they want to know how you observe the velocity of that truck right there, okay? So velocity is the velocity of the object that is moving, and this had a negative sign because it was going the opposite direction, okay? So minus 45 miles per hour, and you need to take away from it every time it saves. It just goes high wire. Take away your velocity. So minus 45 miles per hour. What does it mean? It just means that the truck is going to the left, opposite the car. That's all it means, that minus. That's all the meaning of that minus. Okay, we're getting there. Now, what is the next question? The next question says velocity of the truck from the car's perspective. So, right here, this is the observer now, and they want to know the truck. Okay, so we're doing the velocity of the truck from the car's perspective. So that velocity is going to be the moving object. Who is moving here? The truck is what is moving for us. So minus 45 miles per hour. And we need to take away the velocity of the observer. The car is the observer here. So take away the 56 miles per hour, do the math, and you get minus 101 miles per hour. So the driver in the car, when he sees the truck, observes the velocity going towards the left of 101 miles per hour. That's what it means. Okay, we're not done, I don't think. There's one more. Yep, there's one more. So the last questions is the following. Velocity for the car from the truck's perspective. So let me erase a tiny bit more. The observer now has become the truck. I'm going to do it in blue. So this is our observer now, and they want to know the velocity of that car from that perspective. So the velocity that the truck sees, the car moving. So who is moving now? Our car. And if you remember, that was a positive 56. I know that right now it disappeared, but it was a 56 miles per hour. And you need to take away the velocity of the observer. So minus 45 becomes positive. So what happens here? Instead of a negative, you can have a positive 101 miles per hour. And that just means that the truck observes the car going towards the right with this velocity. That's what it means. Okay? Hopefully this makes sense. That's relative velocity, depending on who is observing the moving object. Now I think it's going to be your turn problem to practice this. Not yet. Okay. Acceleration. Okay, what's acceleration? Well, that's the change in velocity over time. So velocity was meters per second divided by seconds. Your new unit is going to be the meters per second square. Okay? So because velocity was a vector, acceleration is also going to be a vector. And we need to take into account going which way? Positive, right. Negative, left, up, positive, going down, negative. So when you're doing this, you also need to take into account the direction. Let's see. We said that acceleration was a change of velocity over time. How does velocity change? Well, you can speed up. If you speed up, you change the velocity, you have acceleration. Velocity can slow down. The car can be slowing down. That changes the velocity. Slowing down changes the velocity. That means you have acceleration. It's deceleration, means the acceleration is for slowing, but it's still acceleration. You also can have acceleration if you change the direction. So the velocity is changing direction. If you change direction, what are you changing? You're changing velocity. So if you change velocity, you're changing acceleration. 3 scenarios that give you acceleration. Now, you're going to be doing another experiment on page 24. And I just put here to remind you to do your experiments. Let's look at the last example for today. That's found on page 25. It says a car is moving with a velocity of 25 meters per second. Driver slams the brakes and the car comes to a halt in 2.1 seconds. What is the car's acceleration? Oh, we're going to have 2 of them. Let's start with the first one though. Okay, so let's go here. Clear page so we can solve this. And then you're going to have some to do on your own. So what is going on? Let's see if I can get a white pen. I have a car. My car is going east with a velocity that is of 25 meters per second. Then it halts. Halt means it comes to a stop, okay? And it does that. The time is 2.1 seconds. They want to know the acceleration. The acceleration is what? That's all the information we have. Well, what is the equation for acceleration? We said acceleration is a change in our velocity over time. What is a change in velocity? That means final minus initial. You also could write it this way, okay? Sometimes you're going to see it like this, final, and sometimes you're going to see it with a 0. And if you see a 0, it also means initial. They are the same thing. Over the time it took to do that, okay? So those two are the same. This is what acceleration is. Do we have the information to know how to calculate this? Do we have final velocity? Do we have initial velocity? Well, they do give us this velocity. They also tell us it stopped. So when they say it stops, what does that mean? It means that this is our initial velocity, okay? That our final velocity was 0. Because it stopped. So we do have enough information to find acceleration. It's a thinking problem. You have to think what they're giving you, but what they're not giving you is by words. They're actually giving you information. Think what it means. So let's solve this. Let me erase this part right here so I can put all my numbers in. So my acceleration, I said to you, it was my final velocity, 0.0 meters per second, minus my initial velocity, 25 meters per second, divided by the time that it took this car to do this. Do I have the right units? Yeah, it's in seconds, so I can put that in my equation. Put all this information in your calculator. Just put it in. And if you do the math, you are going to see that your acceleration is minus 12 meters per second. And that just means that you are deaccelerating. You're slowing down, which makes sense because you're stopping. Okay? The negative just means you're slowing down. Now, let me clear this so we can do the second part of this example. When objects are dropped, they fall straight down with an acceleration of 9.8 meters per second square. This right here is gravity. Sometimes I forget to put this, the square, so bear with me, but know that acceleration always has these units, meter per second square. Sometimes I forget, but you need to put it in there, and I'll try to remember to put it in there. If a ball is dropped with no initial velocity, then how long would it take to accelerate to a downward velocity of 11 meters per second? Remember that drawings are your friends. So let's draw what they're saying. Something is dropped. There you go. It's going down. They give us the acceleration, 9.8 meters per second. Remember that if it's going down, it's a negative value. There's no initial velocity. So velocity initial, when you started, the initial velocity was 0. Okay. And then it says, what else will they give us? How long to accelerate to a downward velocity of 11? So we know our final velocity is 11, but it's going down. This velocity is going down, so you already can give it a sign that's negative 2. I'm putting it, the book doesn't sound a bit different, but I want you to start thinking this way, because we're going to see these a lot later when we do forces, that you're going to have to give it values, negative or positive values, because of the direction. So start thinking this way. Train your mind to think this way. Going down means negative, just put that value there. Okay? So that's the information they give us. And now they want to know how long. How long means what? It means time. They're asking for this, the time. This is the question. How long? Well, write down the equation that puts all of this information together. Acceleration is the change in velocity divided by time. From here, I can find my time. So my time is my velocity divided by the acceleration. Remember, this goes on the other side multiplying, but then the acceleration is bothering me, and I need to get rid of it by going on the other side dividing. So this is the formula that I'll be using to calculate my time using all this information. Okay, so let me erase some of these so I have some room, and I'm going to put it in a different color so it's a tiny bit easier to follow. So my change in time is my change in velocity. And what is that? My final minus my initial divided by acceleration. That's what it is. So let me erase this right here, because I already modified to tell you what a change in velocity is. And I can put everything in, because I do have everything. So what is my final velocity? Is that minus 11? I'm not going to put meters per second, and just it's meters per second, minus my initial, so minus 0.0, divided by the time it took, the acceleration for this object. Okay? Because we're trying to find the time it took to fall. So velocity final minus initial divided by the acceleration, minus 9.8. You see, I told you that I keep forgetting sometimes to put square. Meters per second square. These are all meters up here, okay? So if you want to remember, these are meters, you're going to end with seconds. So the change in time, if you put all of these in your calculator, you can put this in parentheses, those brackets in your calculator are parentheses, divided by this number, so you end with a negative divided by a negative, the time is going to be positive. And the time right here for the second part of example 1.6 is 1.1 seconds. It took this object 1.1 seconds to fall. Okay, with this acceleration and end with this velocity. Okay, so now it's going to be your turn to practice this kind of problems. You will be doing this 4 and 5. The problems to do that. Okay. I'll give you the answers. If your answers are correct, you don't have to look and see how I solve this. But if you have problems with it, just check to see how it's solved. So let's see. 4 and 5. Start with 4. The answer is minus 1.10 minus 3 miles per second. Okay, this is your answer for 4. And for number 5, okay, that is the final velocity equals 16 meters per second. Okay, so if you did right, you don't have to watch to see how the problems are solved. But if you have problems with it, watch to see how they are solved. Let's move on to new page. Let's start with new page. I want a new page. Okay, so 4 reads like this. 4 reads like this. It says, while driving, a man slows, we're doing 4, okay? Number 4. Slows down his car from 72 miles per hour to 65 miles per hour in 1.8 seconds. What is his acceleration in miles per second square? Well, what are they giving us? Slows down from. From means that was his initial velocity, 72 miles per hour, to, that's his final, 65 miles per hour. And they give us a time. It took this man 1.8 seconds. Okay? And now they want to know the acceleration. So acceleration in miles per second square. That's good because they give us miles per hour. That's the question. What is acceleration? Is the change in your velocity divided by the change in time. That is final minus initial divided by the time. The time. Okay, the time. So we do have all the information you need. That's 72 minus 65 miles per hour divided by, that's going to be, let me see, did they say they wanted in miles per second? What's going on here? We had hours and hours and now we have seconds. That's going to be a problem. You see that? So this needs to be changed. You need to be careful with units. Please be careful with units. They want the answer in miles per second square, and this is in hours. So the first thing you need to do before you can use the formula, okay, is change this. How do we do that? Well, you know how to do this, okay? You open your factor level method, okay? Yellow, I'm gonna go back to yellow. And you can, if you already know how many seconds are in an hour, I'm gonna tell you because you're gonna have to use this in the future. You have 3,600 seconds in 1 hour. The other one, I'm gonna do it a tiny bit different. So you see, you could do it directly if you know how many seconds you have in an hour. Sorry, I wrote this in the wrong spot, didn't I? Oh, okay. I'm trying to get rid of my hours. Okay, let me see. It's correct, but you cannot see it like this. So I'm gonna erase this so you can see what miles per hour mean. Hopefully you have done this in math, but it means this. You had this, miles per hour. Okay, these and these are the same. So now I can put that. 1 hour is 3,600 seconds. Okay? So don't get confused. They give you the information like this, but that means this, miles per hour. So the hour is right here, so I can cross it, and I can be left with my seconds. And if I do this, this velocity is the same as 0.020 miles per second, which is what I'm going to need to do, use here for my acceleration. Now, another way of doing this, let me erase. Sometimes I think, maybe I should not go over this because they probably have done this in math, but then I think, well, maybe I should because they may not know. So here you go. Let me write this as a fraction, miles per hour. Okay, so if you don't know the conversion factors between a second and an hour directly, you can go and say, okay, 1 hour is 60 minutes. 1 minute is 60 seconds. See? So the hour is gone, my minutes are gone too, and I'm left with the seconds. And if you multiply 60 times 60, that's where the 3,600 came from. So everything that's on the top multiplies, and then you divide by 60 and divide by 60. You use your parentheses, and it's a lot easier. So you see that the 60 miles per hour becomes 0.018 miles per second. Okay, see? So you have to be careful. You cannot mix units. You have to use the right kind of units. I'm going to go back to yellow so we can put it now in here. My final velocity was the 0.018, and then my initial was the 0.020 miles per second. Now I can divide by my time that's in seconds, and that was 1.8 seconds. And this is where the value of number 4 came from, that negative 1.10 to the minus 3 miles per second. You put in the calculator, that's where your answer comes from. And it's negative minus 1.10 to the minus 3 miles per second because it's deaccelerating. You see, it went from a higher velocity to a lower velocity. So that's number 4 for you. Let's do 5 to finish. So remember that 5 was asking for the final velocity. And the problem read like this. Let me open it up so I can read it. What will be the final velocity of a car that is initially moving? So initially, they're giving us the initial velocity, 62 meters per second. And accelerates. The acceleration is also given to you. It's a negative acceleration, means it's deaccelerating, meters per second square. And the time that it takes the car to do that is 9.2 seconds. Okay, that's the information for this problem. And they're asking for the final velocity. Where is this coming from? Well, you know that acceleration is a change in velocity over time. You also know that acceleration, then change in velocity, is final minus initial. And then you have divided by time. I don't know why I put that in there, but we're getting to the end. I guess I'm getting tired, but here we go. Time. Okay. So here is where you find your final velocity. We need to isolate this from the formula here. How do we do that? Well, this is multiplying, goes on the other side. This is dividing, goes on the other side, multiplying. So acceleration times the time equals velocity final minus velocity initial. Am I done? No, because I need to have my velocity final by itself. I said to you to get rid of anything that is minusing. You need to go on the other side as a positive. So let's do that. Acceleration times the change in time plus initial velocity is going to be my final velocity. And this is where you now have the equation that allows you to calculate the final velocity. You have isolated that final velocity. That's the final velocity. And do we have the information we need? Yep. Do we have the right units? Yep. So we're just ready to rock and roll. Here we go. I'm gonna go back to white. Make that line again. So my velocity final is my acceleration. Okay, what is acceleration? Minus 5.0, multiplying my change in time, or the time it took, 9.2, and then I need to add my initial velocity, plus 62. Okay, and I didn't put units, I don't have a lot of room, but you do, because you have a page in front of you. So if you put all the numbers in your calculator, if you put them all in, you'll see that that final velocity is at 60 meters per second. I mentioned a minute ago. That's your answer. Okay, that's where it came from. Okay, this is the end of the first half of your module 1. You're gonna need to read your textbook for this section, add to your notes if you need to, review your examples if you need to. You're going to work through all the on your owns for this section as you encounter them and correct them as you go. You don't want to make the same mistake over and over. And you're going to find answers to the on your owns at the end of the module. Study for your conceptual weekly quiz is going to be about the information we covered today. Do all the labs assigned for this section. And then study for a test if you have a test. You're not going to have a test right this minute, but in a couple of weeks, you're going to have a test, okay? And it's usually assigned with the first half of a module. Okay, I hope you all have a good week. Bye.